Welcome to my video. Today's lesson is going to be a quick lesson on the arc length of a circle. Now, the arc length of a circle is different than the arc measure of a circle, and we'll be talking about that as we move through. So before we get going on the arc length, I just want to briefly talk about area versus perimeter of a circle. As we talk about arc length, it's going to be important that we talk about the perimeter of a circle. So we know that in the world of circles, the perimeter has its own fancy name known as the circumference. So anytime we mention the circumference of a circle, we just mean the perimeter of the circle. That is the total distance around the circle. This is measured in what are known as linear units, such as feet, centimeter, meters, any type of just basic units. The formula is the big part. The formula for the circumference of a circle is 2 pi r, where 2 is just the number 2. Pi is pi, which is approximately 3.14, but we'll be using the exact measure using our calculators. And then r representing the radius of the circle. And we know that the radius is the distance from the center of the circle to any point on the exterior of the circle. So as we talk about arc length, what we're really going to be doing is talking about a simple portion of the circumference. So arc length, the definition here is the distance along an arc or a portion of the circle that is created by two radii with a central angle. Now, let's actually see what that means. So we zoom in to our circle here. Let's go ahead and just put the center approximately here. So it's created from two radii, so any segment that goes from the center out to the side. The arc length is then the length of the arc that connects them. When we're talking about the arc length, we're actually going to be talking about how long this piece is. So we're not talking about the measure, even though that will be important as we move forward. We'll be talking about how long this section is. We know that between two radii, this angle here is known as the central angle, and we're going to represent that as theta. We also know that the measure of our arc, so let's just call this A and B. So we know that the measure of arc AB would be equal to theta as well. What we're going to be looking for, though, however, is the length. So not the measure, but the length. But this is important as we find our formula. So theta represents to how much of the circle we have. We can actually set a proportion. We can say we have theta, and we know the total amount of degrees in a circle is 360. So we're setting up a proportion here. What we want is how much of the circumference do we have. So the total circumference is going to go on the bottom. And we actually use S to represent arc length. That seems a little odd. That's because this whole shape here that kind of looks like a pizza slice is known as a sector. And when you look at the area of the sector, that'll make a little bit more sense. And so we use S to represent the length of the arc that creates the sector. So S is going to represent arc length here. What we've just created is a proportion that is going to allow us to find the length of this segment. So if I actually zoom out, you can see that I have that written here as well. So the central angle over 360, this tells us how much of the circle do we want. And then this actually tells us the length. It's what percent of the circumference will give us the length that we actually want. Because we see that this is just a portion of the overarching circumference. Now we can go ahead and isolate this for S. We know that an equation typically has what you want isolated. So I can do that using kind of cross multiplication here. It's going to give me S times 360 equals theta times 2 pi r. And then to get S by itself, I'm going to divide by 360. So there's multiple different ways to write this. I honestly prefer this method, and that's what I'm going to write in my box. And I prefer this method because it helps me it reminds myself that what we're doing is just saying what percent of the circumference are we taking. If that's what you think of arc length as just a percent of the circumference, then using this formula really sets that idea up. It's saying what percent of the circle times the total circumference. Now, you can also simplify this. Sometimes you'll see this written as theta 2 pi r over 360. When we do it this way, we see that we have 2 on top and 360 on bottom. That reduces down, and it gives us S equals theta pi r over 180. In our next unit, when we move into trig, we're going to talk about something known as radians, which is another way to talk about degrees. When we look at that definition, we can see that what we're doing here is taking a different formula, taking the most basic formula for arc length and converting it from radians to degrees. Now, if you haven't learned about radians yet, that is something we can dive into later, but just showing you the two different formulas. As we keep solving, I'm going to use this formula just because, like I said, I think it makes a lot of applicable sense. So let's see what some of these problems might look like. So this one is asking me to find the length of AB. So it's asking me to find actual S. So when we're talking about the length of an arc, we're representing that as S. So I'm going to start with my formula. S equals theta over 360 times 2 pi r. Now, if that's what I'm solving for, I know that I need to find theta in my problem, and I need to find r. So as I come in here and look, I can see that theta was given here as my central angle. It's that angle given right here between my two radii. And r is that length of the radius. So now we can just plug those in. Oops, we have a value for r now, which is 5. Okay, this is where just using our calculator is going to come in handy. I personally like to do the fraction first, so I'm going to do 150 divided by 360, and that gives me approximately 0.416 repeating. Now, in my calculator, I'm just going to carry that number, so I'm not rounding, and then I'll multiply that by my 2 pi 5. So multiply by 2 pi 5. If you are using a TI-84, you're going to see that pi is the blue character above the little caret top. So on the far right-hand side, you have the clear button, and then the caret button, which is your exponent button. The blue character above that is pi, so you can hit second caret, and that's going to give you your pi. Now, if we go ahead and hit enter here, we get that our arc length is 13.09. Now, because this is a length, I want to check my problem for units. I know that lengths are being measured in meters, so I'm going to add that on to my final answer. All right, so it's a very basic, straightforward problem. Let's see what it looks like when we start finding different pieces. So for this one, it wants me to find the central angle for AB. So I know that I'm actually trying to find theta. So once again, I'm going to start with my formula. S equals theta over 360 times 2 pi r. I personally like to rewrite my formula to isolate the variable I want. So the first thing I'm going to do is move that 360 up. Now to get theta by itself, I'm going to divide by 2 pi r. You could do this during the solving process if you wanted. I like to do it on the front end just so I know what I'm looking for and how to plug it in. So in order to solve for this, I'm still going to need to find my r value, which is given right here. But this time I also need my s value, which is given out here because this is representing the actual length of the arc. And now we can plug those in. Theta equals 18.84 times 360 divided by 2 pi 9. Now, putting this in your calculator is going to be important. I personally like to go ahead and do the top first. I'm going to do 18.84 times 360. And then when you divide it in your calculator, it's really important that you put parentheses around your entire denominator. So I'm divided that by open parentheses 2 pi 9 close parentheses. If you don't put those parentheses here, it's just going to divide by your first thing and then multiply by everything else. So it is really important that you're putting parentheses to divide by the entire denominator. That gives us a theta of 119.9 degrees. And here, because our formula is set up in degrees and we're talking about the angle, I know that my final answer needs to be in degrees. That is the unit for the angle. All right, we have one more basic example here as we look along. So once again, it's going to ask me to find the radius. I personally am going to reset up my formula. So S equals theta over 360 times 2 pi r. And I'm going to isolate the r. So I know I need to get rid of the 360 first. And then everything else is being multiplied here by r, so I'm going to divide all of those to the other side. Now we just need to plug in our pieces. So I'm looking for S. Once again, that's actually the arc length. So that's given to me out here, 1.57. I need theta this time. Well, theta is given right here. It's 45 degrees. Everything else are just numbers. So we are ready to set this up. I get 1.57 times 360 over 45 to pi. Similar to the last problem, I'm going to do the numerator first. That's just my preference. And then as I divide by the denominator, I'm going to make sure that I put parentheses around everything. So divide by 45 times 2 times pi, close parentheses. And that tells me that my R is 1.998986. That's the first place I get to round easily, so I'm going to go ahead and round that all the way up just to 2.00. Once again, this one, oh, that's an ugly. It is a measurement, so I need to double check my units. So I'm going to go back into the problem, and I see that lengths were given in feet, so I'm going to add that on to my final answer. All right, so those are some different ways that we could solve these problems out. These ones were all basics, where they gave us a diagram, and we were just finding the pieces that need to be put into our formulas. The next part is, what type of application problems can we do that are related to arc length? So I've got two, I think, application problems here for you. Okay. So this one here, it says a skateboard wheel has a diameter of 56 millimeters. Before I go anywhere else, I'm just going to break that down. I know that my radius is half my diameter. So 56 divided by 2 is 28. 28 millimeters. Now later I see that there's meters in the problem, so I'm going to go ahead and convert that to meters as well. So I get my radius is equal to 0.028 millimeters. So I moved my decimal 3 places for millimeters to get 2 meters. Oops. All right, now I'm going to go ahead and finish reading the problem. It says, how many revolutions does the wheel make while traveling 3 meters? I need to kind of break this problem down. So if you have a wheel, as it rotates, we know that it's also moving in this direction. I like to consider this almost an unraveling. If you were to follow one point all the way around as it rotated, that distance that it goes is actually your circumference. So it almost unravels here if you think about it. Obviously, we know that our tire tread or whatever is not unraveling, but the distance would be as if it did, as if this was a string and as it laid it down, or a rug, it kind of unraveled as you went. So the big thing to know is that one revolution gives us a distance of one circumference. So what this is really asking is, how many circumferences are there in 3 meters? That's really what the problem is asking us here. And now there are multiple different ways that you could solve this problem. And some of you guys may have jumped into different methods, and that's awesome. I'm just showing you one possible method in doing this. So the first thing I did was I figured out, well, what is the length of one circumference? So I said C is equal to 2 pi r, which we know is 2 pi, and we have our r from above, 0.028. When I did that, I got 0.1759 approximately, and this is in meters. So if I'm trying to figure this out, I'm going to do 3 meters divided by the circumference. It's going to tell me how many revolutions I actually did. So I actually did 17.05 revolutions was our final answer here. So some different things, but this is a key piece in solving problems like this, is understanding that one revolution goes a distance of one circumference, because you've fully gone the distance of your circle, you fully unraveled it, and then you're starting over. So this is a type of problem that you might see when dealing with arc length. Here's one more, let me make sure, yeah, one more arc length problem for us. So it says a circle has a circumference whose length is 25 pi. So I'm going to say the circumference is 25 pi. We also know that that's equal to 2 pi r. It wants us to find the length of an arc, so we're trying to solve for s. So I know I'm going to use the formula s equals theta over 360 times 2 pi r, whose central angle is 90. So I went ahead and gave us that part. So we can go ahead and fill in what we have. We know that the central angle is 90 degrees over 360. Now at this point, I'm sorry, I didn't mean to put an equal sign there. At this point, you're thinking, oh, we must need the r, so we could use this to solve for r. And we could use this to solve for r, but what we really need is 2 pi r, and we know that exactly is 25 pi. So we're just going to go ahead and make that substitution. We know that the circumference is 25 pi, so we can go ahead and just plug that in. Because remember from the very beginning, what we're doing here is what percent of the circumference. So the 90 over 360 is telling us what percent of the circumference. We were already given that value. So now we just need to calculate that. 90 over 360 is 25%, so 90 is a quarter of a circle, and then times 25 pi. And that gives us approximately 19.63. Now in our problem, it didn't tell us our units, but we know that we're dealing with a length, so we are going to go ahead and put units as our final answer. And that is how you can tackle problems that deal with the arc length. So this was the arc length, and it's just finding what portion of the circumference.